I'm Dr. Hu. So, meeting students. Okay. How are you guys doing? It's just like say, recently there's so many cases, just take care of yourself, okay? So anyway, so we still can learning and teaching online, so that is still good. So well, okay, so I'm start the lecture now. So today we are going to talk about the liquid chromatography, okay? So for liquid chromatography actually covers a very wide range of different analytical techniques. So, but there's one thing in common is that, so the mobile phase now is liquid. So you guys have learned so many things about the gas chromatography. And starting from this week, so we'll focus on the liquid chromatography. Actually, this will be the main topic. So for the rest of this semester. So let me see, still many students coming. Yeah, okay. We may be interrupted at the very beginning. Okay. For this part, I just want to remind you, because like say for your midterm exam, we already finished. That is gas chromatography. I think Dr. Wang should have already told you guys. So the part that covered in the midterm exam will not show up in the final exam. So that means for the final exam, so what you're going to see will be all the knowledge or all the information you have learned from my part. So, and that account for just 50%. The final exam only account for 50% of your total marks, because you have 30 marks coming from the midterm exam. We also have another 20 presentation. Okay, for group presentation, I think we're going to have it probably in the first week of April. That is actually the last week of this semester. So, and since we're going to have the online teaching for the rest of this semester, so this one will be conducted online as well. So I'm going to give you guys the topic for selection. So later I'm going to make that announcement in the class, and then we'll do that on BU Moodle, okay? And then I will create a forum, and you guys can, I will provide you the guideline and details about topics, and so you guys are going to form your group, okay? Form the group, and then I'll tell you how many groups should be formed, and then you can pick the topic, and then do the group presentation. And I also will give you the assessment rubrics, okay? So we'll talk about the details later on, but don't worry, the point for me to say that now is because just want to let you know, final exam only account for 50%, okay? So on my part, and then another 20% coming from the oral presentation. Well, okay, so now we're going to start talking about the topics I'm going to cover in this part. So we see the high performance liquid chromatography, the liquid chromatography actually can be divided into different categories. The one that you guys have seen that most is actually partition chromatography. So partition chromatography is one that used a lot, the most common one, most popular one. So please mute yourself. So for this one, and also absorption chromatography belongs to the high performance liquid chromatography. And then so later on, we'll talk about the ultra performance liquid chromatography. So, and this one actually has a much better resolution and sensitivity and efficiency than this conventional HPLC. And why is that? Yeah, we can keep that in mind. Later on, we talk about so the parameters that influence the plate number and the separation efficiency. I think after that, you already have some idea, and then it will be more easier for us to go through to explain the principles in UPLC. And that is one category. The other one also includes a size solution chromatography. Yes, this is also a kind of LC because the mobile phase is liquid. And for size solution chromatography, it can separate into the water soluble one and water insoluble one. If it's water soluble one, so it's mainly dealing with those protons. And if water insoluble one, mainly dealing with those that dissolve in organic solvent, like those like polymers, okay? So for size solution chromatography, you can tell from the name. So this is actually, the one that is separate based on the size of the molecule, not really like say by the interactions of the analyte. So with the mobile phase and stationary phase. Like for this one, for the HPLC, we know it involves the analyte, mobile phase, and stationary phase. So the separation really depends on the distribution of the analyte. So between the stationary phase and the mobile phase, right? Okay, is that one. So for ion chromatography, it's also, we're going to spend, I think more than 3 hours on that. So, and this one, so it's quite useful for the separation of those, especially the acids and base, especially those inorganic ions. So there are different kinds of ion chromatography, and the separation really based on the electrostatic interaction between the charged stationary phase and also the charged analyte. So if we're using ion exchange chromatography. So that is actually what we're going to focus in ion chromatography. We are focused on ion exchange, but we also will mention some ion exclusion chromatography. That one can be used for separation analysis of carboxylic acid, okay? So, and then we move on to capillary electrophoresis. And capillary electrophoresis can also handle ions. It can actually different from ion chromatography. For ion chromatography, if you want to separate, analyze cations and anions, you have to use 2 different kinds of columns. They have to run like separately, okay? Please mute yourself, okay? So check your microphone and mute yourself. Let me see whether I can mute all of you. Yeah, and let me see, 1 minute. Okay. Okay, great, okay. And for this one, however, for capillary electrophoresis, it can handle the positive ion and negative ions simultaneously. So if we have some special treatment, it can even separate the neutral compounds, okay? So this is the one like say, maybe not, many of you have used or heard that before, and is you have learned that, but maybe not really use it. So it's not really popular in the testing lab. So, and for affinity chromatography, this one, so see whether we have time. So if we have time, so we'll spend time talking about this one. But this one is quite easy. It's like SP column, like similar, but this one is for bioanalytical separation, and it depends on some very specific interaction between the antigen and antibody. Like one is most popular ones. So, and this one, so it's reversible, it's quite specific. So anyway, so this one we'll see whether we have time. So if we have enough time, so we'll talk about that. But actually what we have covered, so in HPLC, absorption partition chromatography, UPLC, size solution ion chromatography, and capillary electrophoresis, there are a lot of information, okay, lot of content. So we are not really in a rush. I want you guys to understand really. So instead of say putting everything in, okay. So well, we'll talk about definitely working principles. So and how each separation technique works, the theory behind, and also definitely we'll talk about the applications, especially so when I'm talking about the partition chromatography, this part, HPLC part. So I'm going to use several examples. And for some of you, you have taken the courses like I taught on Monday. So we're talking about the sample pre-treatment. So for those of you who didn't take that course, no worry, because for the partition chromatography, when I'm talking about the different cases, I'm going to talk about, we're going to do that kind of practice. We're going to do the practice starting from analyzing the chemical property and structure of the compound. Because the purpose for me to give you the example, real case example, is like say, I hope like later on, so when you encounter the similar problem or something in your research or your work, when you look at this compound, you can apply the knowledge you learn from this course. You look at the chemical structure, you tell what kind of chemical property it has, whether it's polar or non-polar, and does it have any like chromophore? And then so you can decide, so what kind of column you can use for the separation and what kind of detector is most suitable for it. Okay, and then we also will start from its chemical property. We think about what kind of solvent we can use for extraction, and if we want to do some sample cleanup, and what kind of SPE column so we can use to clean the sample and then to do the pre-concentration. So this is what we are going to practice. So in this course, we're talking about HPLC after we talk about all this theory, okay? So that's the main idea. Okay, so that's enough for this overall introduction. And now we'll move on to HPLC. Okay, so today we're going to talk about very basic things about HPLC. So about the development, and also we talk about some detectors that have been used. So I hope today, so we can finish probably until like slide 66. So, and because later on, after that, we'll, if we look at the notes, so we're going to talk about all the factors that influence the separation efficiency of HPLC. I hope, like say, when we talk about that part, you're not really tired, your minds are very clear. So that's why I want to talk about that part next week at the very beginning, so when you're very clear, because that's very important, because that's a kind of essential point information for you to understand so the development of HPLC. So why UPLC is better than normal HPLC, and then why we kind of say because of this improvement of development of the HPLC column, so that kind of facilitate or much widen the application of the HPLC in analytical science. Okay, so anyway, so we talk about this one. Let's first look at this one. So the liquid chromatography was actually defined in early 19th by the work of the Russian botanist. So what happened to this guy? So what happened for this guy is just like say, so here's a botanist, so he just uses some solvent to extract some of those plant leaves. And then so after extraction, so what happened? So he just like packed a glass column with powdered chalk, as is calcium carbonate, and some aluminum, and then he put his sample like this one, so into the column, and then followed by some pure solvent, and then he put the pure solvent, and then so as the sample passed through the column, so by gravity, and he observed that different color band developed and separated. So, and this is actually the first discovery of that kind of liquid chromatography, and why the compound can be separated. At that time, actually here, it's just like this one, this guy just used a glass column. The glass column is pretty large. It has an idea of about 5 centimeter diameter and much bigger than the current HPLC column. And then the length is actually about, say, it varies. It can be like say 0.5 to 5 meter long. So it's pretty long. So that's why, so it's very slow. So, and then the compound just like kind of like flow out and then has separate. And the reason it can be separated because the mixture contains so many compounds. So, and they can partition differently between this moving solvent. This moving solvent is called mobile phase, okay? And also the particle, so which is called stationary phase. So that means the analyte, they have different distribution between this mobile phase and stationary phase. And because of its own different chemical property, polarity, for example, and then so, and that's why. And because different color have been seen on the column, so like join that, so that's why it's called chromatography. Okay, so it's chromatography. Chrom means color, graph means right. So that's development of that. Okay. So when we talk about liquid chromatography, it actually can be either in a planar form or a column form. So the planar form is like thin layer chromatography is the most simple one. So, but today we'll talk about the thin layer chromatography briefly, okay? The reason we want to introduce it because even now it's still very simple technique, but it's the most kind of like expensive and convenient technique still used a lot in the lab, especially the pharmaceutical lab or Chinese medicine lab. They use it as a preliminary method to kind of determine or develop so the separation condition. So later on that can be applied on the colon separation on the HPLC colon. So this one is trying to develop the optimal condition so that can be applied on colon. Okay, so and then we'll talk about so how to do that. And then so then it becomes the gravity chromatography. That is what we just mentioned about. So this the Russian botanic. So he can develop this one. And however, so what people found is like if you're using this chromatography, because the particle at that time, so the packing material size is 150 to 200 micrometer. And then so, and also if we're just using gravity, the flow rate is so slow. So then people think about, how about I give it some pressure? Or how about I using a pump to pull it through? And then that could be faster, right? But however, so what they found is like, they found like saying, the color efficiency is not good. It's not good. So the peak shape is not good then. So the reason so for that is because at that time they don't know, but actually it's later on people found that. So it's because the particle diameter of the packing material of the colon, okay, is too big. So if the diameter, the dP of the packing material, say dP, okay, of the particle can decrease, okay, and then so that can make the separation efficiency much better. So that comes to the development of the HPLC. So at that time, so here, so the particle size is just like say 150 so to 200 micrometer. So and then when with the development of HPLC, so that becomes like say so 5 to 10 micrometer, much smaller, and then can even go down to 3 micrometer. And then so then now because the particle gets smaller and more tightly packed, so that's why you have to apply a high pressure to make the sample and mobile phase go through. So that's why the high performance liquid chromatography so also require high pressure. But because the dP, the particle diameter, decreased a lot, and then so that makes the peak shape so sharper and separation more efficient. Why is that? I'm going to explain that. Okay, so and then so in 2004, people further decreased the diameter dP, further decrease it, okay, to 1.7 micrometer. Oops, got to bring this closer to myself. Okay, 1.7 micrometer. So that makes like even efficient. Okay, so and we'll talk about that. Well, before we talk about colon chromatography, we're going to talk about the planar chromatography. We say the thin layer chromatography is the one we commonly use, right? Okay, so as what you can see here, so the sample is actually spotted so onto the plate. So on the plate, it's actually coated so by a thin layer of chromatographic particles. So it can be silica gel or aluminum. And then this one is the thickness. It's the thickness normally, it's not the diameter particle. It's the thickness of that so layer of this thin layer. So how about these particles? So the particles have different sizes. So and if nowadays people using the particles also pretty small. So if a particle has diameter so less than 5 micrometer, so it's quite efficient. Okay, and then so but however it does not really have some high capacity. When I talk about efficient, it's compared with the original, the paper one. Okay, so but still cannot compare with the HPLC one. Okay, so and then fixed on the surface of a glass plate, and then this is something like maybe some of you have seen that before. And then you can see, and then what you need to do is to draw a line, use a pencil to draw a line, so about 1 to 2 centimeters away from the bottom, okay, on the bottom, and then you can apply the sample. So when you apply the sample, it's pretty critical. So, and then the solution is normally diluted. It's normally about, say, a sample is about 0.01% to 0.1% for this sample solution, okay? So it's solution. And then you add it on that. And every time, so use a capillary tube to add on one. So you don't want the spot to be like larger than 5 millimeter. No, you don't want it. So, and if your concentration too low to dilute, so you add it like multiple times, but each time you just apply that. So sample dot and wait until dry and apply again. So, okay, if it's too dilute, you do that multiple times. So once you have done that, and then, so you're going to put it into a closed tank. And this one is called solvent tank. Okay, it contains the developing solvent. And then you put the end with the sample application. You immerse this end totally into the solvent, but you have to be very careful. So you don't want those sample dots to contact the solvent. Okay, no, so above it. And then so enclosed, and then wait. So, and then the solvent, so will migrate along this plate. And this flow is created by what? This flow is created by capillary action. So as the solvent is diffused into the dry particle layer. And then so once they pass through those sample, and then so they kind of migrate. So the analyte, the compound will migrate together with the solvent. And some, like say, dissolve more in the solvent and then they migrate faster. This is the solvent front. You can see that. This is the solvent front. And some migrate faster, and that yellow dot, and some migrate slower, like the blue dot. And by that, okay, so we can calculate actually their K factor, retention factor. So, okay, and from that, I think all of you must be familiar with what is the retention factor, right? So you've known that. So in Dr. Wang's lecture, so you should know that. So retention factor, and then can apply that later on to the column. So this is basically how that works, okay? And so how can we read the thin layer chromatography? So it's not like GC, you read about retention time. No, so there's no retention time. So what we read is about, you can measure the distance. So what we read is the retardation factor. Because what you can measure is you can measure the distance between the analyte and the starting line. Okay, so we call that DR, the distance between that. And then you can also measure the distance of the solvent front to the starting line. We call that DM. M means mobile phase, okay? R means reagent, right? Okay, the analyte, we can call that. And then so, and the ratio for that is the retardation factor. So DR over DM, okay? So, and for this one, I mentioned that for the best separation efficient, and then so you don't want to apply the dots like too big, okay? So you want that to be kind of small. And then for the measurement, so sometimes those compounds, they do not really have color. You cannot tell that by your eyes. So how to visualize those compounds. So we often use the fluorescence. What means I say we can mix the fluorescence material together with those coating material. Okay, and then when organic migrate, so when it reaches point, so it can quench, so that fluorescence, and then when we expose the plate in UV light, and then we can see the dots, and then so we know that. Okay, so this is how that works. And then so if we do some simple calculation to understand the RF, still remember what is RF? RF DR over DM. Okay, so you can see now. So how to tell what is in the unknown compound? So here it actually applied 5 dots. So this is pretty common practice. When we want to see what is unknown, if you have some idea of the candidates of the compound in that, you can actually apply the authentic standard. So at the same time on the same plate. So in the middle, this one is unknown compound. And then, so in this experiment, the student think about maybe the unknown compound contains compound A, B, C, D, maybe one of them, two of them, I don't know. So I will see that. So the student applied dot A, dot B, dot C, dot D. Now represents to the authentic standard, the standard that you can buy so from the company, okay? Or you can synthesize by yourself and by the 2 sides, okay? So, and then do the development, okay? So, and we say the distance is from the center of the spot moved divided by the distance solvent front. Now we can see the solvent front. What is dm now? Dm is here, which is 5 centimeter, right? Okay, so how about the RFA? Now look at compound A. So how about the GR of A? I think something wrong here, right? Okay, so here should be the A. Is something wrong here? So here should be, okay. So A, dr of A is 2. So it's 2.0, right? Okay, so we have 2.0 divided by what? Divided by 5.0, I got 0.4, right? Okay, so how about for RFB? RFB, this one, so it's 3.0 divided by 5.0 equal to 0.6. So you can do that. And then you can do C, how about you do that by yourself? 0.8 divided by 5. What is that? So it's 0.16, right? And you also do D, so it's 4 divided by 5, so which equal to 0.8. Right, so that's what we can do. We actually can do that calculation and we get A, B, C, D. Okay, and then so we look at the 2 dots that are separated from the unknown compound. We can see one, so it has the same dr, okay, and therefore the same RF, so equals 2, so 0.16. The other half also the same dr of 3 and the DRF of 0.6. So we kind of preliminarily determine that. So this unknown compound contains what? Contains, so which compound? Can you tell me? So it's compound C, right? And also compound B, right? Okay, but preliminary, because why we say that? Because this one is actually quite qualitative. So maybe sometimes some compound, 2 different compounds, so they may have the same RF. So in the analysis, if you really want to confirm that, so you need to have some extra method to confirm. So this is exactly compound C and compound D, compound B. Okay. So what we can do is like say you can scratch this dot out. Okay, and you do the solvent extraction. And then so you do the filtration and then you can analyze that in HPLC or in LC, in GC, depends on so the polarity or volatility of the compound. And then you can see from the structure and the mass, whether it is that compound you're interested in or not. It exactly is compound B or compound C, okay? So that's how that works, okay? So the different variables that actually can influence so the RF factor. So in, for example, the thickness of stationary phase, because that means it's really related to the capacity and how fast it can move, right? The moisture content of mobile phase and mobile stationary phase, the temperature, sample size, and pre-saturation of the solvent vapor. What is that? Pre-saturation of solvent vapor. So you see, it shows you. So as we just mentioned, we say, okay, after you applied the analyte, your sample, probably you just directly immerse the one end into the solvent. But here, if you pre-saturate it, it's like say, now you have the a closed container. So you already have the developing solvent inside. And the closed container already put aside for a period of time. So inside the container, so the solvent vapor, okay, so already like say, already in this container. So, and then so what you do is like you can put the plate so into the container without touching the solvent, you put aside and let the plate itself to be equilibrium with the solvent vapor first. That means a little bit for a period of time. And then, so you put that into, immerse one end into the development solvent and let it to have the development, okay, of the analytes. So that is allowing pre-saturation of the layer, so with the solvent vapor. And that does help with the separation. You can see, and this one is the one, so with, let me see. This is with the saturation, and this is without saturation. So, and you can see a better separation, right? Okay. So, because we already mentioned there's so many different parameters that can influence the RF value, the separation of the analyte. So, and it's kind of impractical. So it's kind of impossible to keep all the experimental conditions exactly same. So while you're doing the thin layer chromatography. So that's why, so the method of TLC is more considered as qualitative analysis. And then so it's not really that accurate. So it's kind of expressed as, because this value is dr/dm. So nothing can travel faster or more than the solvent, right? So this value is kind of within, so 1 and 0. So probably can equal to 1 if like whole retain, no retain, like that one, okay? So it's not moving at all. So it's between, so 0 and 1 anyway, so it's within that range. So, and it expressed as the value, so better not more than 2 significant digits. That means I say, because it's not really that accurate. For example, we say the RF value equal to 0.10 or 0.16. That's enough. Don't say 0.165 because the last digit actually not meaningful at all. So because it's method, so it's not really a very accurate quantitative method. Okay, and as we mentioned that, so sometimes for different compounds, they may have the same so RF value in the round. So, and also the result may not be reproducible. So, and if you want to really give a very confirmed identification of this analyte, of this unknown compound, so you have to do further analysis or further identification. So, as well I mentioned that you can just like scratch that spot out and then do the further extraction with solvent filtration and then analyze by other more accurate so analytical technique such as mass spectrometer and so on. Okay, so and because of their kind of their experimental condition may not be exactly the same all the time, so that's why so standard reference is always recommended. So on the same plate for comparison. So for that one, so your results actually can be corrected by this standard, internal standard. So the migration for that one, so sometimes you will see Rx. Rx means the relative retention factor, right? Relative retention factor. So it equal to the distance of the center of the unknown spot to the distance center of the standard, like say dr over d standard, right? So, and it's try to overcome the variability, that means of the RF value, that means overcomes the influence of the uncertainty of experimental condition. Okay, so And there's some requirement for the internal standard that added to the mixture. It's better if you can have a similar chemical nature, and also, so it's better that if the RF value is in the middle range of the unknown compound. Okay, so and by using this ratio, so I kind of hope eliminates the variation. This is similar concept as we're using our internal standard in GCMS, right? Okay, so I think Dr. Wang should have mentioned that before, right? So you can using the internal standard by that one. So you can take in the ratio so of your, even when you're doing the calibration curve, right? You can using so the mass fragments used for the analyte and normalized by the mass fragments. Right? So you use for internal standard and then do the calibration curve, and also later on do the quantification. Because even you're using it in automatic injector in GC, and sometimes the injection may not be exactly the same. So, and using that internal standard, so you can correct for that injection so variation. And also if you spike the internal standard at the very beginning, I mean for GC and LC analysis, so you can even using that one to correct for all this kind of sample loss while you're doing the sample preparation, right? Okay, but anyway, we'll do recovery as well. So this is just mention that it's something similar concept, similar idea. Okay, so to overcome that variability. So therefore, we can see that because the THL also has the mobile phase, also have the stationary phase. Okay, so we can use in the stationary phase that similar to what you're going to use in the column, and then mobile phase similar, and then to see which compound so runs fattest, which compound is the most reluctant to be separated, and then so and we have the guide so for the development of the optimal condition for performing separation on the column chromatography, okay, on that. So the retention factor, if we see that, so it's actually expressed as so dm minus dr divided by dr, because so we see the retention factor RF equal to dr over dm. If we divide dm both on top and bottom, so we can get the retention factor K equal to 1 minus RF divided by RF. Okay, so here I have a YouTube one, but let me see. What is that one I put in before? But anyway, so we explain this one first, okay? So why we get this one? Anyone have any question about this part? Do you still remember? So what is the retention factor when Dr. Wang talked to you guys? So retention factor, what is retention factor? It's a small k. So equal to, anyone tell me? You don't want TR minus TM divided by what? Divided by TM, right? So because before when you are learning that for gas chromatography using retention time, right? Retention time. So retention time of the analyte minus the retention time of the mobile phase, and then divide by TM, and you get the retention factor. But here, how can we get that one? What we can get is only what? Only the distance. Only the distance. Okay, I probably draw here. Okay, the distance of what? As I say, it's the starting line. We get that this is your sample, your compound. So we only get dr, and you get the solvent front, the solvent. So you get dm. How can we relate dr and dm to T? Okay, so from distance to time, if we can know the speed, the linear velocity of the mobile phase. Okay, for example, if we say if u is the linear velocity of mobile phase, okay, of the solvent, here. So, and we should know the time it takes for the solvent to travel from the start point to the end point, right? Okay, so let's define it. So let's define the TR and TM. So TR, what is the TR? TR is for the compound, the time for the compound to go through the column, right? Reach the detector. And TM is a time that for mobile phase to go through the column to reach the detector. That means TR and TM is a time for the analyte and mobile phase to go through the same distance, right? The column. Understand? So here, so we can assume the same thing. We assume that TR now is the time, so for the analyte to go through the DR distance. Okay, TM is the time for the analyte, for the mobile phase to go through the same distance. So TR and TM, so we can see, then correspond to the time for them to go through what? To go through the same distance, DR. You can see that one. I have this one. So the time required for the mobile phase and to travel through the fixed distance DR. So, and then how can we correlate them? So we only know U now. I only give you the U, velocity of the mobile phase. So how about the velocity of the analyte? How about we say UR? Can we say that? Can we say that? Yes, let's assume that. So what happened is, I know, so the time for the analyte to travel through DR equal to DR divided by UR. Am I right? Yes, okay. But also remember one thing. So the time for the analyte to travel to DR, and where is the solvent at that time? Can you tell me? So by the time, so the analyte traveled to DR, what is the distance? So the solvent has traveled, DM, right? Okay. So by the time, so the analyte traveled to DR, the solvent already traveled to DM. So that means the time for the analyte go to DR is equals to the time for the solvent to move to DM. So that's why, so DM divided by U equals to DR divided by UR. Am I right? Yes, right? Okay. Because now we do the separation. So for the same time, so analyte stop here, solvent stop here. Okay, that is good. So we already know this expression. How about TM? TM means what? TM means the time required for the mobile phase to go through DR distance. Okay, that's easy. Mobile phase goes through DR distance, just the distance divided by velocity. Also DR divided by U. Now we can get, so TR minus TM divided by TM, we just put them in. Can we? Okay. Yes, okay, very good, thank you. So, and then, so we put them in, and then, so we rewrite this equation. Okay, so now I replace TR here, because now TR equal to DM divided by U. And then I replace TM here, because it's DR divided by U, okay? And then, so here also TM. Okay, now they all have the term of small u velocity. Can we cancel that? Of course. We just cancel them and we get K prime equal to the retention factor equal to DM minus DR divided by DR. And then, so if we want to know retention factor from that one, This is what we get. Okay, and then so you can just like divide both of them up and bottom by dm, so you get the retention factor K equal to 1 minus RF divided by RF. Now, do you have some idea why we say that we can use it to kind of develop the optimal condition? Now, later on, we can apply on the column, because in the column, so retention factor kind of indicates so how well that compound so can be retained or separated, right? Okay, so not really just this one, together with the selective factor as well. So right, okay, so because we know that resolution, this one, do you still remember that? Just refresh your mind, equal to relate to the plate number square root, oops, and times what? Selectivity factor alpha, right? So you will see this again later on when we talk about how we can select the solvent for HPLC, and times what? Times the retention factor, okay, this part, and this involves inverse reaction, okay? So you can see that this one really so related to the resolution. And from that, from the RF, you obtained here on thin layer, so chromatography, if you use similar stationary phase, similar mobile phase, you have some estimation about this K value, okay? So this is how we do that. So actually from this K value, and you can, from this, the DR value, so you can also kind of estimate, so the plate number, even like, so on this TLC, okay, so the column thin layer chromatography, yeah. So, and then that is just for information. So, and for the plate number, not really in column, okay, so plate number, so in the thin layer chromatography, okay, so it's also can be estimated by N equal to 16 dr divided by W, so square. I mean, what is W? W is here. So, and then, so this is a dot. And then this is a dot, sorry, I should not use in the solvent example, which is this analyte. So this is a dot. So it's not really a small dot, it will develop, right? So it have some width. Oops. So, and then the distance is its width, okay? I hope you can see. This is its width, okay? So, and that is how wide it is. So this is that. And then, so also you can estimate the plate height, which equal to dr over n, sorry. So this is just for information, okay? I only hope that you understand how we can derive the retention factor K prime from RF. Okay, so far, everything is okay. So you can follow, right? I hope you understand this part. Understand? Okay, so if no question for now, so we move on so to the column chromatography. So this is the, after we're talking about the plate chromatography and you have idea about so why the thin layer chromatography now is still like used in many of the lab to do the so preliminary test. So now, but in the realities, like say the column chromatography is the mainstream. Okay, so as we mentioned, in a conventional column chromatography and the particle diameter for packing material, this is DP for packing material because the column is packed column. Okay, so those things. Okay, for the packing material, it's pretty large. It's 150 to 200 micrometer. So that's why. So it has very low flow rate. That takes long separation time. So that's why people think about how about we give it some vacuum? How about we give it some pressure? So does it help? Does it really help? So, and then, so apply that. But remember, do you guys remember? So the Van Deemster equation, okay? This one, okay, a big tick, right? Plate height and also the velocity, okay? The velocity, so of the flow rate, and then we see, and also we made to ABC, plate height equal to A plus B is one velocity plus C, right? Okay, so that's why when the velocity, so speed increase, and the C term, this one, everything increase, right? And then what about that one? If the speed increase, how about plate number? So how the plate height? Okay, so H also increase. So if H increase, how about N? N equal to L divided by H. So N decrease. If N decrease, what happened? Do you still remember what I wrote here? If N decrease, how about resolution? Resolution decrease, right? So that's why. So what happened is like, if apply this one here, so it caused the decreased efficiency. And then, so what can they do? Later on, people found that, well, actually, DP play a very, very important role. So if you decrease this DP, so a lot by a large order, and then so that can dramatically, so greatly, so decrease the plate height, and then so that can really so increase the so separation efficiency, and then so that's what we mentioned about. So now it becomes the development of high performance liquid chromatography. Now the stationary, so they requires very small particles, very much smaller particles. That's why it can have a better separation. And then, however, it requires high pressure to force the mobile phase to go through the column. And this is so picture for the HPLC, and we see that it's not like GC, it has different modules, right? So you have the mobile phase module, flow rate composition, the module, injection, and column, oven, temperature container, and also the detector. So different module pile up together. So, and now we are going to talk about exactly the details about the column HPLC. Okay, so how about we stop here now? So we stop here. How about we just take break for 5 minutes? Okay, so what time is it? Now it's, so we come back at 7:58. Okay, so about just like 5 minutes. And then so the next break also will be 5 minutes, and then so we can stop a little bit earlier. So not really early, it's the same time. So but not 9:50. We'll stop at 9:40. Okay. So.
Recording stopped.
Okay, so we'll start again.
Recording in progress.
So if you take an overview of LC, so we can kind of tell what kind of LC technique we can use. So depending, I say, on the chemical property of the analyte. So first we can tell the polarity. So whether the compound is water soluble or water insoluble. So if it's water soluble, you can kind of tell whether it's ionic or say non-ionic. If it's ionic and if it's not really a huge, big one, so you can think about ion exchange chromatography. And or maybe you can just like say make it to be a little bit neutral and still polar, and then you can think about like using the normal partition chromatography to do that. Then you say, we haven't learned that before, so I don't know what is the normal partition. So I don't know what is reverse phase partition. That's okay, we'll talk about very soon, okay? And then so for water insoluble one, so you can think about kind of absorption if it's nonpolar. But anyway, however, so we can see that it can also separate, depends on its molecular weight. It means like for very big molecules, so and the normal HPLC we're talking about, not really suitable, okay? So what we do is like say we can using the side solution chromatography. For the water soluble one, we normally say also proteins. Okay, so we can use the filtration, the gel filtration. But for those like organic soluble, so and for water insoluble ones or lipid soluble, we call them so gel permeation. So this is more often to use for the analysis of polymer. Okay, so that is what we're going to talk about. First, we have an overview of the LC, and so we see what is the absorption chromatography. Absorption chromatography is not really commonly used right now, so it still have some application, especially when we're using them for separation of some of the isomers. So it's relatively polar material with high specific surface area, so which is used for stationary phase. And then the silica is being the most popular one, but also the alumina and magnesium oxide, they can be used as well. So it's like say the stationary phase most time is solid, and the mobile phase relatively non-polar, can be hapten to the THF, okay, the tetrahydrofuran. And then so for this one, for absorption chromatography, so it's polar compound, so eluted later than non-polar compound, because if it's the silica particle, so itself has OH, so stepping out, okay, so it's the silica particle on silica themselves, like say bridging this O bridge, and then they also have the OH functional groups sticking out, and then so this one makes the silica particle itself actually is polar, okay. So, and then so the polar compound will retain more on the stationary phase, and then so that'll be looped later. So partition chromatography actually is the one so we used a lot, okay. And then so later on we'll talk about more so about this one. So but now overview for partition chromatography. So now the liquid stationary phase is coated on the inert solid support. So in a solid support, so it's chemically bonded for this liquid stationary phase. So it can divide into either reverse phase chromatography or normal phase chromatography. It really depends on. So, and on the silica particle, what it can do is like say, it can be so chemically bonded. How to do that? Example, so this is silica particle, OH. So it has some reaction with those chlorinated dimethylcellulose. So, and this is the tail. This is the stationary one we want to support. Okay, so and that will make the silica particle chemically bonded and derivatized to be a stationary phase that we want. CH3, CH3, and then for R. For example, so if you want a C18 carbon, and what is R? So R will be carbon 18. So there will be like many carbon chain like this one, done 18 of them. Okay, so that will be C18. So, and if you want a C8, and then that means now the functional group, like say at the end will be R. Understand? So this is how, so the reverse phase is made, and this is reverse phase if it's done. So you can see for the reverse phase chromatography, so the stationary phase is very nonpolar. For example, the C8, C18, and the phenyl group, and so on. So the mobile phase is relatively polar. It can be water, it can be THF, and most of all we can see sometimes we use ACN, use a lot, and then methanol, that is often used, right? ACN, methanol, and THF, so they are all commonly used. So the solvent. And then, so how about, and the polar solvent such as water, so will elute more slowly than less polar solvent as acetonitrile. What does that mean? So how about I give you one example. So, and if we're talking about reverse phase, we talk about C18. Now I have compound A, B, C, okay? So I say the polarity for those compounds. Polarity of the compound A more polar than B and more polar than C, okay? So now it's the C18 column. This is the time, okay? So now I have 3 peaks coming out. Okay, so I have elution order 1, 2, 3. So what is 1, 2, 3? Tell me, compound, what is the 8, 1, 2, 3? So elution order. So who comes out first? Who comes out second? Who comes out last? What is that order? So it's the C18 column. The C18 column means the stationary phase is what? The stationary phase is relatively non-polar. So what compound will like more likely to be in the non-polar stationary phase? So do you want to type in the answer? CBA, using CBA, or another answer? This is a non-polar one, okay? Non-polar stationary phase will retain the non-polar will retain more tightly, right? Okay, so the polar one will not be either, like say, because now the mobile phase is more polar, the stationary phase is very non-polar. So the polar one will like mobile phase more or the stationary phase more? You'll have the mobile phase more, right? Okay, so you're more eluted out by the mobile phase. It has less retention on the stationary phase. So that's why. So we'll have, the result is, sorry, A, B, C. So the polar compound have least retention on C18. So the less polar one, the non-less polar one will have a longer retention, strong retention on C18 will comes out lost. Okay, understand that one? Okay, so because A is more polar than B, is more polar than C, but now the stationary phase is non-polar. So like dissolves like, right? Okay, so the non-polar one will like more, okay, I like the non-polar stationary phase, I want to stay it longer with it. Okay, but not for A. A is more polar compound, so it travels happily together with the more polar mobile phase. So that's why it loses out first, and then so followed by B, followed by C. Okay, so now I change to another solvent. Okay, still ABC, but now they look like this one. So still have. So the peak comes like closer to each other. So may not be exactly like that, just like to illustrate, okay? The peak comes like closer to each other, especially may not be too much for A change, especially for C. So I have to see the retention factor, the K, retention factor. So for C, office becomes smaller. Okay, so decreased. And then I just change the solvent. Now I give you a choice. I have two solvents for these two applications. 1 and 2. Okay, so case 1, case 2. Now I have two solvents. I have solvent, I have water used in one of the case. I have ACN used for the other case, the ACN for the other case. So can you tell me? So, and case 1, case 2, which case used ACN as the mobile phase? Think about it. Which one used ACN as mobile phase? Because first tell me which one is more polar, water or ACN? Which one is more polar? Water is more polar, right? ACN is less polar. Yeah, thank you. Thank you for your response. Okay, so thank you for all of you like response in the chat room. Okay, so water is more polar. ACN is less polar. So now, so C at the very beginning, C like to stay in a stationary phase, say, I'm not really polar. I like the non-polar stationary phase. I want to stick together with it. Okay, but now the mobile phase changed from water to less polar ACN, let's say less polar. So, and then the C, because it's not that polar, so, and now it become mobile phase less polar, and C will more likely, do you think C will more likely to dissolve and to be in water or ACN? Definitely ACN, right? Okay, so yeah, very good. So ACN now have a stronger elution power, we can say, to elute C out, to elute the less polar compound out. So that's why you see in case 2. So not really much change for A, but for those, especially those compounds are very late in chromatography, if we switch from a polar solvent to a less polar solvent in the reverse phase chromatography, that can really help to wash out those less polar compound come out from the column. Okay, so that's why. So here in this term, so in the statement, you say a polar solvent. So here, case 1 using solvent, so using water, and case 2 using ACN as mobile phase. Okay. Okay. So that's why this statement say a polar solvent such as water elutes more slowly than less polar solvent as ACN. Because now in this case, because ACN is less polar, and now because you need to elute the less polar compound, so on the stationary phase, so that's why ACN has a stronger elution power. If we're talking about, so normal phase, if we talk normal phase is opposite to reverse phase. For normal phase, and now the stationary phase will be polar, and then the mobile phase will be relatively non-polar. Okay, so, and if we're talking about the normal phase, let's see, how about we talk about that now? So here is for reverse phase. Reverse phase. How about we talk about normal phase? The normal phase now, so the stationary phase is polar. Okay, so now the stationary phase is polar. And now the mobile phase is relatively non-polar, okay, has lower polarity. We can say, let's see, mobile phase is, I'll just say less polar. Like for the stationary phase, it can be something like the diol. So that means OH, and 2 OH functional group on that, okay? Or cyano or amine, okay? Amino, something like that one. So it can be polar. And then so the mobile phase less polar can be hexane. Okay, so it can be like methylene chloride. Do that. Okay, and something like that. Okay, so and if that is the case, if now I'm using the same example here, So A, B, C. So do you think, like, say, which compound comes out first? Still, A is more polar, then B, then C. Now I have normal phase. I have normal phase, which have a polar stationary phase. And then you think which compound will be more likely to be in the stationary phase? Which one is least possible, least likely to be in the stationary phase? So which one comes out first? Which one comes out last? Now it's CBA. Thank you. Very good. Now it's CBA. Okay. So, oops, sorry. CBA. Okay. So now you can see. So the less polar one will come out first because now it's polar stationary phase. So it does not like the polar stationary, it will not retain on it. And then A is more polar. Now you see the polar stationary phase. Oh, like this looks like. So it one stays there, okay? So and the mobile phase is less polar, so it does not really have the very strong illusion power, right? Okay, so for this A, so that's why, okay? So, and for the other one, if we change to another, say, different polarity of the mobile phase, you can keep it as something you think about at home, okay, after class. I leave it as a counter question for you. So how about we change the polarity of solvent? So how can that influence the elution, the speed? So the retention time of say K, okay? So retention factor, how will that influence the retention factor of the CBA? Okay, so don't worry. So it's something you can think about first, but don't worry, later on when we talk about Cartesian chromatography, I will definitely explain that one more time. So in this part for normal phase, and then you'll get the answer. Okay. So good. So and we just like here, we just do something like just explain something a little bit more to you. But there are other LC, so which is ion exchange chromatography. So ion exchange chromatography, the separation is based on the opposite charges on the stationary phase and mobile and the analyte. Okay. So the stationary phase normally can contain ionic groups such as the tertiary amine. If tertiary amine is positive, or sulfonic acid. So they're very strong. So they're kind of strong. What? So for this one, if the stationary phase is positive, so what kind of ions is going to retain? If it's positive, it's going to retain negative ion or positive ion. Let me know that. Okay, it's going to retain negative ions. So it will going to retain what? It's going to attract, so have electrostatic interaction with ionize. Okay, so if this one, so is sulfonic acid, so it will have the strong interaction with cations, right? Okay, so and so that's why if it's the quaternary tertiary amine for the stationary phase, so it's an ion exchanger. So if it's the sulfonic acid in the stationary phase, then this is what is cation exchanger. Okay, so it's interaction between this ionic group and also so this on the stationary phase and also the ionic group that's on the sample molecules. Okay, so this one, so actually in this class when we're talking about SPE, we also talk about a lot about this one, right? Okay, so we can play with several parameters to adjust the charge. So like the pH, okay, and also for the elution, we can think about the ionic strength. But don't worry, we'll talk about that later on when we talk about ion chromatography. There'll be much powerful and more detail about ionic chromatography than we just covered so in SPE that part. Okay, but so and for the mobile phase, definitely because you want to break that interaction between the ions and stationary phase, right? Okay, because you want to elute them out, you want to separate them. You don't just want to bind them, so you want them elute out one by one. Okay, so that's why. So most cases for the mobile phase, they are either acid or base. Okay, so and which one use acid, which one use base, and what is about pH range and other things we have to pay attention to. How about stationary phase? Don't worry, we'll cover that in ion chromatography. And for ion pairing chromatography, and this is a technique we use less, okay? So use separation for ionic compound as well, but however, those compounds, they may be large, so they may have some problems. So secondary, for example, they may be large, they have some hydrophobic tail, so that may slow the mass transfer or may have the secondary hydrophobic interaction with the stationary phase of the conventional ion chromatography. So, and then if that is the case, because for this IC, we want the separation to be just a pure electrostatic interaction between the stationary phase and the analyte. Okay, we don't want any of this hydrophobic interaction like that one. So no, okay. So, and for ion pairing, it's dealing with those compound, problematic compound. They may have some hydrophobic tail, so that could interact with, have secondary hydrophobic interaction or something like that. So they will apply some reagent to mask the charge, and then they either treat it like something like say C18. So well, anyway, we'll talk about that later. So, but for this one, it's not as popular as the ion exchange chromatography. Okay, and for size solution chromatography, so basically, so it's very simple. The separation all by size according to the molecular weight. So we can even use this size solution chromatography to determine the molecular weight of the polymers. So, and we'll introduce that introduction while we're talking about the SEC. But as you can see, demonstrate in this figure, we can see that for the small molecules, they're able to travel into those. So because the stationary phase with those porous materials. So they have different size of the pores, and then so for the small molecules, they can travel into the pores, and then they took much longer path to go through the column. But for those large molecules, they're too big. They cannot diffuse into those pores, so they cannot, they're totally excluded. So they took the shortest path to go through a column. So that's why the large ones comes out first, and smallest ones comes out last. Okay, so the largest one comes first, and smallest one comes out last. And for this one, everything based on size. So that means we don't want any interaction between the analyte and the stationary phase. No hydrophobic interaction, no electronic static interaction, no, not at all. Okay, so we just want no interaction at all. So it's just based on the size, and then that determines how long they travel through the column, and then how long the time they have to use. That's it. Okay, so that's overall. If we look at that one, so this one, the table kind of shows again, so about so what kind of chromatography we can use for, again, so this one just put that into the table. So again, for molecule size smaller than 2000, again, we think about whether it's soluble in water or soluble in organic solvent. If in water, if it's ions, so, and especially those in organic ions, we can use in the ionic exchange chromatography, but for some small acids can use that as well. So, and this is for non-ionic water soluble, can think about those normal phase, and here give it to you. The soluble, if it's organic hydrophobic, more hydrophobic, not this is hydrophilic, this is hydrophobic, okay? If more hydrophobic, and then so if it's soluble in moderate polar one, so, and we can think about a normal phase, but if it's in, say, less polar one, so, and then we can think about, that means quite hydrophobic, think about the reverse phase chromatography, okay? And if it's much larger size, and then if it's soluble in water, so that is for, can think about size, so filtration chromatography, so gel filtration chromatography. And if it's, like say, if it's more soluble in organic solvent, and so we can think about the permeation chromatography, okay? So, well, and there's different separation techniques. So sometimes, like you guys, when you are doing experiment, when you're looking at one compound, so it's very natural for you to think about it. For example, when I'm looking at this glucose, this is chemical structure. 1, 2, 3, 4, 5, 6, right? Okay, so, and it has this kind of the shape, okay? So, and and it has OH group, sugar compound, right? Okay, so if you have this one, and you have to think about, well, which technique I can use for the separation. So, and which criteria should I use to do the determination? Okay, so now let's see. Now you have GC and LC. And how can we make the decision? First, we need to talk about the sample volatility. So everything based on the chemical property of the compound. So is there a particular requirement for HPLC volatility? Not really, okay? So HPLC doesn't care, so really like volatile or something. It's just like say, because now the mobile phase is what? The mobile phase is liquid. So liquid requires what? Solubility. So that means your analyte must be soluble in the mobile phase. Okay. But however, how about for GC? GC now the mobile phase is what? Carrier gas. The gas carry those compounds to go through the column, right? Okay. But though that means that your analyte now in the gas phase. So, but you inject solution. So that means they have to evaporate. They have to turn to be the gas in the injector. So that means your compound need to be volatile. If they're very polar, if they're long volatile, so they cannot evaporate. They just like accumulate, stock the column, right? Okay. So GC requires something volatile. Okay. How about polarity? HPLC and separate both polar and non-polar. I already mentioned that. Depends on reverse phase or normal phase, right? For the normal phase, and then so retain more polar compound, reverse phase, better for those the less polar one, right? Okay, so it can be, and also we can even ionic is fine. So we can using the special type of HPLC with ion chromatography, right? So and even for those small one for the HPLC, we can also nowadays they develop like say helix column, different types of column. The helix one can also using to separate those small acid and base and so organic acid, okay, of course, and so on. So and how about for GC? GC because everything needs to be volatile. So if you have very polar functional group, that will decrease the volatility so of the analyte, make it less volatile. So and then so that's why GC so prefer something less polar or even non-polar. If we have polar compound, so you have to do derivatization. Do you know what is derivatization? Derivatization means like say you want to do chemical reaction to change the polar functional group to less polar functional group. For example, for sugar compound, we also have those sugar compound in environmental sample. So in my group, my students also use GCMS to analyze the sugar compound, glucose. So, but they're not really directly analyzing it because the glucose, it has OH group. So, and this hydrogen, so on this OH group is called active hydrogen. So we don't inject this one into GC. Okay, so you want to replace, so this active hydrogen, so by something like less polar. Okay, so that's why we do the chemical derivatization with BSCFA. So and then so the H, this one, the high active hydrogen now is replaced by the TS methyl silicate. Okay, so we do that. So this is how we do that. We do the derivatization to convert that one. You do that functional group. So we this means something compound group here. Okay, so and it has OH group, and then so the active hydrogen is become so TMS derivatized. And then so you can see that we call it TMS, and then become much less polar functional group. And then so it can be analyzed by GC. So that means you have to do derivatization to convert the polar functional group to be less polar functional group. So if you look at this one, so you can see, so if you look at x-axis is volatility, y-axis polarity, okay? So polarity go up, that's more hydrophilic. Polarity go down, that's more hydrophobic. Volatility if go here, so if long volatile, more suitable for HPLC, volatile more suitable for GC. For those non-volatile and hydrophilic inorganic ions using IC, sugar, normally we use the HPLC. But okay, so if you see something, you see TMS derivatized sugar, and that can greatly change the polarity of sugar after derivatization, become much less polar, and then make it be more suitable for GC. Okay, see that. And then for other things like say and antibiotics, fatty acid, and then so aflatoxin and then amino acid, more suitable for this side. And then so for nitrosamine, and then so epoxide, essential oil, this is very volatile. So you can smell the perfume, right? So and hydrocarbons, they're often analyzed by GC. Okay, but if you want to analyze fatty acid by GC, same, you have to do the derivatization. And how about others? How about the thermoliability? Do we have to consider about that? For HPLC, does it matter? Not really, right? Okay, but when we do the HPLC analysis, we not really operate at very high temperature. No, we add something like just like room temperature, can be a little bit above room temperature, but you see, you do not heat up the HPLC column really. So in normal operation, room temperature pretty okay. So some special case, we want to heat it a little bit, say 40 something. Yeah, but for GC, definitely. So we have the injector, okay? So injector temperature sometimes can go to even like 250, 280, that can happen. So, and then it must be survive under this high temperature injection port. You do not want the compound to thermal decompose. Some of the pesticides, so they do not really survive under that high temperature. And then so then the recovery won't be very good. And how about molecular weight? So for HPLC, so no theoretical upper because everything depends on solubility. As long as it can be soluble in the mobile phase, it should be fine, it's okay. But for GC, because we think about the volatility, so it should be volatile. If it's very high molecular weight, the molecule won't be volatile, right? Okay, so that means we typically handle something like less than 500 AMU, okay? So that's the reason for that. So how about the sample preparation? So, and for HPLC, we have to do the filtration because you don't want any particle to block your column. Right? Sample pretreatment, very important. So you have to do the filtration, and also you want to get rid of some matrix dirt, and then you can have the cleaner chromatogram. And then so, and sample should be in the same, it's better to prepare your sample with the solvent that has similar composition as the initial condition of the mobile phase. And for GC, and then the solvent needs to be volatile. You cannot using very polar solvent, okay? So, and generally, because first you have the solvent delay. Remember in GCMS analysis, you have a solvent delay. So you don't want the huge solvent peak get you into the detector. That means the solvent should evaporate so earlier, faster. Okay, so then you analyze. So and then so that means you want to use this less polar solvent. Okay, so for HPLC, the sample size depends on column ID. So and for GC, normally you use 1 microliter. Sometimes 2 microliter. That is already pretty rare. 5 microliter, very, very rare. Okay, so and for the separation mechanism, HPLC involves what? Involves your analyte, mobile phase, and stationary phase. Really depends on polarity of the 3 of them to see like how the analyte so migrate or distribute between these 2 phases, stationary phase and mobile phase, right? So, and however for GC, so mobile phase is just a carrier, just carry gas. So just carry those analyte, already vaporized analyte, to go through the column, okay? So, and HPLC for the detector, most common one is UV visible, but we're going to introduce more detector very soon, okay, today. So, and it has very wide range of non-destructive detector. For GC, so the detector, universal detector, FID, right? You already know that. can be the mass spectrometer, electron capture detector, especially for halogenated compound. So then I won't spend time talking about this one. Okay, so if we further compare the HPLC and GC, so and the diffusion coefficient of the sample in the mobile phase is much smaller in HPLC than in GC, of course. Why? Because mobile phase now in HPLC is liquid. Okay, so the mobile phase in GC is gas. Okay, so also let's say for those, we talk about that Monday as well. So we talk about the diffusion coefficient of liquid and gas, right? So which one has a much larger diffusion coefficient? Gas. Okay, so gas. The diffusion coefficient, if we still remember that, is the we talk about diffusion coefficient. The unit is square centimeter per second. And for a liquid, it's normally at the order of, like, say, 0.2 to 2 times 10 to the minus fifths. Here is 0.2 times 10 to the minus fifths are same, okay? So it's 10 to the minus fifths order for the liquid. Okay, how about for gas? Gas is about say 0.1 to 0.4. So this is for gas. We can see like the gas has much larger diffusion coefficient. Okay, so this is that means that the speed can be much faster in gas chromatography, but at the same time, the diffusion coefficient, because that one relate to the beta of the Van Demister equation, right? Okay, so that can a lot diffusion coefficient will increase the plate height, which is not really good for the resolution separation. But the GC column is much longer than HPLC column, so the total plate number can be large. Well, anyway, we talk about that later. And how about the viscosity of the mobile phase? Yeah, of course, the liquid, okay, is more viscosity is much larger than the gas. Okay, so and this one means what? Because it has the larger viscosity, so that means so this is not really an advantage, because that will result in small diffusion coefficient, also a high flow resistance of the mobile phase. So, and another one is the compressibility of the mobile phase under pressure is negligible small in HPLC, but it's not in GC. This is the advantage, actually, that because that can result the flow velocity of the mobile phase is quite constant over the whole length of the column, right? Because it's not really compressible, and we make it HPLC is safe because now it's under very high pressure. So, and if it's compressible, it has the explosion, so hazardous, the risk. But now it's the liquid is compressibility is not really, it's negligible. So that's why even under high pressure, so it's not really that dangerous. Okay, so if we look at the typical number of separation of the plate, we talk about the per column. We can see that for capillary GC, it has 50 K per column. For HPLC, only like 5,000. Okay, so 5K so per column. But if we talk about per meter, because GC column, the length of this column is how much? 30 meters long. That's common. Some can be even 60 meters long, right? Well, for HPLC, how long is normally an HPLC column? So the HPLC column is much shorter. So it can be just a 15 centimeters long. Okay, 15 centimeters long. So it's much shorter. So, and then even the total plate number is not that. But if we talk about per meter, so it's much larger. Okay, so, and why? So that total plate number is length, right? It's much longer, right? So if you times that. Well, anyway, so let's give you an overall comparison of HPLC and GC. And then so from what we show you guys just now here, so you see that this is a parameter you have to think about. So this is all the parameter about the sample, okay? That means like which method you have to choose depends on the chemical, physical property of the analyte, okay? Of the analyte. From itself, you can tell from its structure, you can tell from its functional group, you can tell from its molecular weight, you get the judgment, and you know, so which instrument you can use, you know which detector may be suitable. And again, you know which solvent may be suitable for extraction and which sample cleanup method. Okay, this is what I mean. Later on, we're going to use some real case study. We're starting from the compound itself. We do this kind of practice. We tell, so what kind of like technique we need to use. Okay, so and then so this is the sugar compound which is mentioned about. So we can use it without chemical dramatizaton. So we have to use HPLC colon, and this is what we use the ammonium colon, so amine colon. So and then we can see, so it has the separation pretty well. And detector RI here. Definitely can use other detector. Okay, so you can use mass spectrometer for sure. And this is the schematic of the HPLC instrument. Let's see what time is it. Okay, so we finish this one, and we take one later. But we can see this is a HPLC instrument. It has the solvent reservoir, the filter, the pump, and the program solvent, and then we sample injection, column, and so on. So this is, you guys must be familiar with. You already have done some of the lab, right? So in HPLC, the particle size range from 2 to 10 micrometer are used for stationary phase. Pump is needed to pass mobile phase through the column at high pressure. The high pressure can be like 1,000 to 3,000 psi. So, and 1 atmosphere equal to 14.5 psi, if that's the case. And then, so this is about 200 atmosphere, this one. So this is about, let's say, 70 something psi. So about 70, yeah. So, and atmosphere, sorry, yeah. So, and we can do either isocratic elution or gradient elution. Isocratic elution means like a single solvent of constant composition is used on mobile phase. It can be, say, 100% water, or maybe just like 100% ACN, or 60% water and 40% of ACN. But mean like isocratic, it means like if this is a composition at very beginning, it will be the same composition. So for the whole separation process, unchanged. Okay. So gradient elution means we're using solvent program. So 2 or more solvent systems that differ significant in polarity are employed, and then they were going to change while we do the elution. At very beginning, we have 95% water and 5% ACN, and then so gradually, so we want to like elute more less polar compound out. So that's why we want to increase the fraction of ACN. So that will help to push those, so more less polar compound in the C18 column out. So we gradually decrease the fraction of water from 95% to decrease probably to like 70%, and then we gradually increase ACN percent from 5% to 30%. It's just like different cases are different, okay? So and then so we hold that for a certain time, and then so after that we get back to the initial condition, and then go back to 95 water and 5% ACN, and then so we keep for a certain time, and then so back equilibrium and start again, right? Okay, so this is means gradient elution. And we can see that so in the solvent, and there are different solvent reservoirs, but there are some gases can dissolve in the solvent, such as oxygen and nitrogen. So they can be dissolved in the solvent and form some of the bubbles. Okay, so what we can do is like, so before you really run HPLC, you want to do degas. What we do is that we have to prepare the solvent, and you want to like say cover with the parafilm, and then we put some hose on the parafilm, and we put that in the sonicator to do the sonication to get rid of the bubbles, dissolved gas into the solvent. And then we put that on the HPLC, but still before you really run HPLC, you want to degas, you want to purge, okay, with the helium, okay? And then you purge that and get rid of the bubbles. We're using helium purge, and then so then you can run the sample. And then also you have to estimate the solvent you're going to use, and then so it's some common rule to do that. So estimate. I'm not sure whether John has mentioned that in the lab course. I guess you must mention that it really depends on how many sample you run, because like sometimes you may have to run the sample for a pretty long time. So you may not just stay in the lab watching it, right? So you may walk away and let it do that by itself. And then you have to have enough solvent to put that in. So it's number of the sample can times the time of the sample for each sample, and the flow rate, and then the solvent percent. For example, you have to say 60% of the methanol. So in this program, so you have 50 sample, each sample takes about 10 minutes, and the flow rate is, like say, 0.9 milliliter per minute. Then you'll be 50 sample times each sample 10 minutes times 10 times, say, flow rate is 0.9 milliliter per minute, you times 0.9, and you times like 60%. Also, you times the factor is the safety factor 1.2, and you plus an extra 100 milliliter, and you calculate that. So, and then that will be the reasonable amount of solvent that you put, so in the bottle, so for this round. Okay, so we can see that if you do isocratic and do gradient, so the response is different. Okay, so you can see that for this is the isocratic elution, and this is a gradient elution. So which one looks better? Obviously the gradient one. Okay, so you can see the same examples using separate the benzene, monochlorobenzene, so chlorobenzene, so on, hexachlorobenzene. So this one's least polar one. Okay, so that's why, so it comes out lost, right? Okay, so and then you can see here, so and if you're using gradient elution, so that'll be much better. So that'll be much better. Okay. And you can see first with more water, and then methanol increase at the rate of 8% per minute. Using more methanol, less polar one to push. So because here you can see if you're using the isocratic, so retention time much longer. It has the larger retention factor, but now you're using that more methanol at the end, so that help to elute it out. Will decrease this retention factor of the especially lost species. Okay. So, and that is for those gas sense. And then how about the pumping system? So there are different requirements for the HPLC pumping system. So, and it requires high pressure. Okay, everybody knows it requires high pressure. At least you have to some pressure that can make it run. And then so required pressure up to 6,000 psi. And then we expect a pulse-free output. And then so I should be able to maintain a stable flow rate ranging from 0.1 to 10 milliliter per minute. And then so we want the flow rate to be precise because that relates to the retention time, right? Okay, so and the flow rate and flow reproducibility need to be like in a 0.5% relative or better. So and also the pump need to be the corrosive resistant, because sometimes we'll add some things in, even like say definitely if you're doing the MSc lab, so John won't let you to add the THF, that is not really favorite because corrosive. But for some of the separation, you may have to add a little bit to help your separation, but you can find the replacement for that. And sometimes we use the acid, okay, or something like base condition, especially when we talk about IC. So that means those things need to be the corrosive, so resistant. Okay, and there are different types of pump. The first one is the most popular one, which is called reciprocating pump. And then so we also have the syringe or displacement type pump, and the last one is the least common one. So we look at the first two ones. So the first one, you see this one is the reciprocating. What I mean is the movement, so back and forth. Okay, so it's described the here is the motor drive piston. Okay, so you can see this one has the chamber, so inside. So this pump, it has internal. The chamber has relatively small internal volume. It's about 35 to 400 microliter inside the chamber. So it can handle pretty high pressure. It can have the motor drive piston here. So you can see this piston can move forward and backward, okay? So when it's pulling out, and then, so because in this chamber, inside this pump, in this chamber, you see two check valves, these two balls, okay? When it's pulling, what happened? The bottom check valve open, and then the mobile phase, the solvent mobile phase gets in, and then they're going to push. When it's pushing, the bottom one check valve seal and the top one open. The top one now is open, and then the solvent goes out. Okay, so by this way, it's just like in, out for this one, pulling, push, pull, push, pull, push. So it has the pump, so it has the things gets in. So it can adapt to gradient illusion. So it has pretty constant flow. So, and we see that it's one of the most common type of systems. So, but it's kind of expensive. It has the two check valves and this piston movement. And because it has this piston moving, pulling and push. So when it's pulling this way, so because the solvent gets in, it's called the filling procedure, okay? Filling stage, fill stage. When it's pushing, so compress the sample, the solvent, and the solvent move out, is called a pump stage. So there'll be a fluctuation of what? Fluctuation of the pressure, right? So we start to, when you start to feel, what happened? The pressure drop, okay? So this is a feeling, the feel stage. We start to pump, so pressure increase and feel, okay, and decrease, pump, increase. So it has this up and down, up and down, up and down fluctuation. So we have this up and down fluctuation because the pump has at least to spend some time for this filling. So, and then this up and down will make some fluctuation of what? The flow rate. And then so that make the peak noisy. This is not really good. That affects the sensitivity and detection limit. That means you have to overcome this one. So people think about, how about we make the filling stage be quick, and then just like quickly, just like say, hey, quickly go down and go up, quickly go down and go up this way. So it helps to reduce this kind of like fluctuation, but not really 100%, let's say. So remove it. So that's why. So, and people have another device. So using the dampener, okay, the fluctuation, the dampener. So you provide. It's also, it has something like also connect to the mobile phase, and then it has also it's piston control. It can have a diaphragm, so that is kind of filter, so separate. So some of the so the inside, the dampener, and also the mobile phase. So according to the outside, the mobile phase, the pressure fluctuation, and then so this dampener itself, it can push its solvent, so push its diaphragm out or in, pull in, push out, depth in, to get its extra pressure or release some pressure, get extra pressure or release some pressure to kind of maintain so the flow to be constant. So this is not maybe beyond the topic. So if you have interest, you can check that one. Okay. So, and this is what we do. But actually, now in HPLC, they have that the dampener. So, and then so that can have to already like correct this kind of fluctuation. Okay. So, and this is another one, the displacement pump. But this displacement pump is not really popular. So, although it's pulse free, but it's like a syringe. So it's like, say, a screw, this one, the driven piston, so a syringe like that one. So it has limited mobile phase capacity, and it cannot do the gradient illusion. So this is not the popular ones, just for information. So, well, how about we stop here? So again, so let me see. Again, so we come back, so at 20:58, okay? 5 minutes break, and then so we can finish at 9:40, okay? So
Recording stopped.
Okay, so we'll continue.
Recording in progress.
Too long, 3 hours. Well, anyway, so let's look at the sample injection system. So there are several devices available, so either for manual injection or auto injection. So, but here, so we see that, so you can directly to put the septum injection. But for septum injection, so you are facing a very high pressure inside. So that is much more difficult. And stop flow injection are really good. So that's why. So nowadays, the one we often use, that one you load and inject, that one is the 6-port loop, so sample injector. Okay, so and this one is most popular because it has inside it has a sample loop, so can hold different volumes of the sample. So vary from 5 to 500 microliter. Injector has 2 modes, so it can be loading position and also the injection mode. Okay. So, and we also call that 6-port injector. It's my pens here, okay? So, and it has pretty good reproducibility, and how it looks like, it's like 6-port. Why you call 6-port is one, okay. It has 1, 2, 3, 4, 5, 6. You can see for the 6-port, each of this port is connected to something. And it has, like, say, port 1 to syringe and sample, and then 2 and 5 connected loop, 6 waste, and then 3 to column, 4 to solvent to mobile phase. And then so this load position and this injection position, you may get confused. Why is that? Okay, so let's do that. We do that for you, like to illustrate that more easily, probably. So we have 1, I do exact same here, 2, 3, okay, sorry, 3, 4, okay, 5, 6, okay. So we do 1, 2, position 2, position 3, position 4, position 5, position 6. Now here is the sample, your injector, your sample in. So the direction is in, okay? So now you have 2 and 5 is the loop, sample loop, different volume. As we can say, it can be 5 to 500 microliter loop, depends on which one you set. Okay, if it's a, I want to inject 20 microliter, and here will be 20 microliter, one connected. And then, so how about 3? 3 is here, is from, oops, sorry. And then 3, actually we go from 4 here. Okay, how about from 4 here? 4 is where you have mobile phase in. Okay, now we have mobile phase. And 3 is connected to column. And then your 6 is go to what? 6 is going out this way to waste. You can see that at the loading position, what happened? At loading position, so I had 1 and 2 connected, okay? I have 3 and 4 connected, 1, 2 connected, gap, 3, 4 connected, gap, and 5, 6 connected, okay? So this way, understand? Is that easy to understand? Okay. So what happens, like when in your load position, sample in get into 1, and then you connect to 2, go to 2 and fill in the loop, go to 5, and from 5 to 6 and to waste. So that means you will inject more than what you need, and then it will be loaded. You inject more and then make sure the whole loop is filled with your sample. Okay, and now mobile phase go through the column. Nothing happened, nothing injected into the column. Okay, now we have the same. Now we do the same. 1, 2, 3, so 4, 5, 6. Now we still have this one, the loop, 2 and 5. Oops. Now we still have the sample syringe, okay? Even though you not inject something, it's okay, the sample. Here still go to waste. Now we still have the mobile phase. And now we still have this one go to column, okay? You can see, right? How about now, after you load the sample, you remember you switch, you rotate the lob, okay? Now I'm going to rotate it. Rotate, how to rotate? I say now I don't want to connect it. I want to rotate. I can do this way, can I? Yes, you can. So what you do is that now I have 6 and 1 connected. You move this way. You move this way. How about I do this way? More correct, more easy to see. We go this way, rotate, okay? Rotate. So 1 and 2 before connected. Now 2 and 5 connected. Okay, 2 and 3, sorry. 2 and 3 connected. And 3 and 4 before connected. No, now they are not connected. So, and 4 and 5 connected. So what happened is now mobile phase get 4 and go to 5 and flush through the column and flush through the loop, okay? And push whatever sample inject into the loop to 2 and go to 3 and directly go to the column, okay? So that's why. So by this way, you get exact amount that already inject into the loop, injected into the column, okay? So this is how that works. So load and inject. So what you do is that after your injection, everything get into the loop and rotate. And then so now be 1 and 6 connected. So the sample directly go to waste. Actually, you're not injecting any sample now. So you already loaded, right? And then so mobile phase, however, mobile phase now connect to the loop. Mobile phase get in and flush whatever in the loop. So to the column. So you get a very precise volume injection. So this is how that works. So and make very convenient and easy to do. Okay. So this is how that looks. And then how about LC column? So LC column, so as many like say stainless steel tubing, so that can handle high pressure. But sometimes if you see some like say low pressure one, a very common one you see in lab, so they have heavy wool gloss or PEEK tubing. So but for the LC column, so it normally should be it's straight, okay? So as normally to 5 to 25 centimeter long. If 5 to 25 centimeter, that's pretty long. So what you normally see is 15 centimeter long. And this one is diameter of the column. That means the ID of the column, okay? C means column, okay? So the diameter column is 4 to 10 millimeter diameter. So it's pretty thin column. And the packing material, particle 5 or 10 or 3 micrometer for normal HPLC, okay? So and then, so that makes the plate number to be 40 to 70K plates per meter. Remember, right? We just saw that number, about 50K. So that is for HPLC column. So and analytical column. But there also be some micro column, if you can tell from the name. Micro means a smaller scale, right? The smaller scale. So the length is about 3 to 77.5 centimeter. So the diameter of the column inside ID is 1 to 4.6 millimeter. So it's thinner, even thinner, okay? And then the shorter as well. So, and therefore the packing material will need to be smaller, okay? And then so, and the efficiency can be even larger, okay? So, and it has much less solvent consumption. And we also, besides a little column, we always so have been recommended, right? So when I'm a PhD student, I always like recommend me to use the God column. Okay, so while we're doing the research now, we're still using God column, of course. That's a common practice. Okay, so why we have to use the God column? So because the analytic column itself, that long is very expensive. It's expensive. Okay, but if we have some dirty things accumulated, so on the column and make your column performance very bad, so you just waste money. You have to like change another one. So, but if you're using God column, so it's much shorter. It has the same packing material as your analytical column, but it's smaller, shorter. So it's shorter. So that's why it costs less money. So, and however, it protects the real analytical column, because if you have anything like say human-like substances, environmental sample, if we have some like residue species not really clearly treated in your food sample, if we have many bulky things like in pharmaceutical sample, so not if we don't have a perfect sample treatment, and then you have some high molecular weight compounds get in, so they will just like accumulate in the God column. So if behavior not good, you just replace it. So and then that protect your analytical column. Okay, but it have the same packing. Okay, same stationary phase, same packing parameter, and then we want to control the temperature of LC column as well. The two basic type of packings, one is pellicular particles. So, and this is what originally used is spherical non-porous glossal polymer beads. So which has the DP of the 30 to 40 micrometer. So it has the thin porous layer of silica, alumina, or so PSDBB, so and coated, so or something like that one. But however, so it has been replaced by this porous particle. The porous particle column is what we commonly use right now. So the porous microparticle with diameter is 30 to 10 micrometer. So which has the narrow size distribution. Now the technique is really good. That means make it to be uniform diameter. So if I say it's 5 micrometer, it's going to be all 5 micrometer, not it's they have very regular shape. Okay, so that greatly increase the column efficiency, also help that one. So it helped for the A parameter. Okay, so in composed of the silica or alumina or PSDBB, so or exchange resin. So the stationary phase is just chemically bounded on this solid support. Okay, so stationary phase we normally chemically bounded on that. And for the exchange, you have the resin is the polymer, so it can be the stationary phase can also coat on that. So, and that's why we say chemically or physically, but most time chemically bounded thin organic film as a stationary phase. So that's how it looks the column. So today most of packing fall into 4 classes. Okay, so there's silica or alumina are bound phase on either alumina silica, so that would mean chemically bounded one, the gel, and also something of the controlled pore loss of silica, that one. So it's for information. So, and if you look at the capillary or microbond columns of those HPLC1, so if we talk about microbond, that means the inner diameter ID of this packed column is even less than 1 millimeter. That is very small thing, right? If capillary is even less than 1 millimeter ID, and then inside even could not be really packed, could be something internal bounded one. So for those columns, so they require much smaller solvent flow, so and much less sample injection. So there are just some new method more to improved, so detector designed to meet that requirement. So and so here just like for information is just something like say the HPLC column, so can be in the capillary or microbond form as well. So this shows the result of separating the aromatic compounds using this microbond column, and the mobile phase is that one. So and flow rate you can see if you're using the micro size or capillary size, it's just for microliter, not like say milliliter. Okay, so 4 micrometer per minute, very small amount, very small flow rate. And then so it can do pretty good separation for this one. So nitro aromatics, and then so injection is 60 nanoliter. So that's very small amount, and using the UV detector as the detector for that one. Okay, so and we can see if you for this advanced technique, so they have reduced sample capacity, but this one they need improved detection to be more sensitive, right? Okay, because they're now very small amount get injected. So and then especially when you are injecting into the detector, if it detects that volume, so that can cause the peak broadening. So and then so that's why for this particular small scale one, so the jet volume must be eliminated. And advantage is also again reduce sample size, you get very minimal amount. So and also you consume very little solvent. Okay, and so it's quite good for that part. Okay, so anyway, so this is for information. So sometimes when we are running the HPLC, and one common problem you may encounter is like say, well, okay, so I do the calibration, everything looks good. My peak shape looks good and well separated, everything fine. But once I run my real sample, after say, suppose the column can use for many times, I see all the students, I'm some PhD student in the group, they did that quite well. But why when I use it? So the column only inject for 50 times or less than 100 times, it gets horrible, the peak. So what happened? My column only lasts for only a short of time, a very short time. So what caused the problem? How can I solve the problem? Okay, so what is that problem? What is that problem? So when you have the distorted peak, when you peak show very high pressure, that has a very high chance is that you get some dirty things get into the column. Okay, so it blocked. So it's just like say the column head is just kind of like blocked. Okay, so what happened here is say that means you have to do what? Sample cleanup. Sample cleanup. You may do more effective the sample preparation technique. Okay, so you can go through your sample through some SP column before you do the analysis. Okay, and what else is like say, I recommend you can use a God column. So if you say I already tried, can try to do the sample pre-treatment, but still, so not really that good, and then use a God column. At least you can protect your analytical column, right? Okay, so sometimes like say we try to flush the column using the solvent you run, but it takes really a long time to do so, and most of the time the result is not really that good, but it's worth trying. You can flush the column and to see how that works. But yeah, but I always say try to, if your sample is dirty, and try to if you already tried all you can try to do the sample cleanup, sample preparation part, so use a God column. Okay, so that may helpful. Okay, so now we move on to talk about the detectors. Okay, so that are being used in HPLC system. So and we have different requirements about the detectors, right? So you want the detector to be what? We want all the detectors so they to be robust, right? So we want the detectors to have good linearity. We have they did have adequate sensitivity, very good stability and reproducibility, and so on. So and well, and we can actually separate the detector according to whether it is based on solute property or bulk property. What does that mean? If I say it depends on solute property, that means it depends on the chemical property of the analyte. So I list a bunch of detectors below. So you think which one responds to the chemical property of the analyte? How about UV visible detector? Yes, because it responds to the chromophore on the chemical, right? So yes, its solute depends on the solute property. How about fluorescence detector? Yes, so it depends on the fluorescence chromophore on the analyte as well, right? So how about IR detector? Yes, because some chemicals are IR sensitive functional group. Okay, so they have different, some may not, but they have anyway. So if I have the IR infrared, so they have different response peak at different wave number, right? Okay, in our using wave number. Okay, and how about the others? How about electrochemical detector? This one corresponds to more to the mobile phase, the property changed, because with the analyte get into the mobile phase, the electrochemical response, the dielectric constant may change, right? How about refractive index detector? This is also with the presence of the compound showing up in a mobile phase, and then so the refractive index, the property of the mobile phase change, and then so that can make it to be detectable. Okay, so and then so this one so correspond to the property, bulk property. So means bulk property means the mobile phase bulk property. So that has changed. So which correspond to refractive index and also refer to the dielectric constants, so on. And if we say solute property, that responds to the chemical property of the analyte itself. Okay, as I say, mass spectrometer, UV visible, fluorescence, and so on, right? IR and so on. Let's look at them. So the first detector we often use is refractive index detector. It's nearly universal, but it has pretty poor detection limit, not really good. Okay, so because we know unlike GC, so LC has not really literally does not have a very universal detector that universally can be applied to everything. Okay, and so we not really as reliable as some FID, so that can be used for GC. Okay, so here for the refractive index detector is nearly universal, and then so and what happens is, see, now it has two chambers. One chamber is for the sample to go through, and the other chamber go to the reference. That means the mobile phase. Okay, so the mobile phase and the mobile phase, so with the sample. So you can see now when the because of the now the compound is showing up so in your sample, so that means it changed the property of the mobile phase. And then what happened is, like, say, because of precise change the refractive index of the solvent, so and then that cause when light gets in, so the instant light will bend. Okay, because we'll kind of say already changed the refractive index, and then so and then we reflected by the mirror gets in, and then will be hit on this photo sensitive surface of the detector. Okay, because of banded, so because of the compound show up, it banded, and then so the location for it to hit on this photosensitive sensor will change, and when it change, measure that variation. So and then so that corresponds to the signal. Okay, so this is that one. But however, it's quite temperature sensitive. So that means when you are using this refractive index detector, it has to be really a very accurate control of the temperature. So and detection limit is 10 nanogram of the analyte, so in the sample. So and then so and it very sensitive to temperature change. So and because this magnitude of the refract index, so and of the thermal expansion of the solvent as well. So another one is more common. This is quite commonly used. Most of the LC we use UV visible detector. So for the UV visible detector, you have two. If it's UV visible, you have two lamps for that. So on UV using the deuterium lamp, so we have the wavelength range from 160 to 375 nanometer. As you have already learned that from the last semester analytical spectroscopy, right? So the visible light is ranging from, say, 400 to 800, right? So the UV light is like below 400 or something like UVA, UVB, UVC, right? Okay, so for visible light using the tungsten halogen lamp that actually cover not only just the visible light, it's also part of the UV light and also so the infrared light. Okay, so and it's tunable wavelengths. We can just like scan the full spectrum, right? Okay, you set the wavelength, scan that, and then so and it can also select the specific wavelengths you want to do the measurement. And if you still remember how to quantify that in UV, we're using Beer's law, okay? What is Beer's law? A equal to epsilon BC, right? Okay, so it's molar absorptive coefficient, and then C, concentration, and then B, path length, right? Okay, so, and we can see here, so this one is using the Z shape for the detector inside. Why is that? Because if it's just like, say, a thin line here, if you like say your sample just pass through this way, and then you can see now the light pass here is very small. It's just like say the diameter of this column. So the B is really small, right? Okay. So, but if you're using a Z shape, now the light path has been greatly extended. So, and if light path be extended, and then how about sensitivity? Yeah, of course. So B increase, that will cause A increase because absorbance, that signal is what you measure, right? Okay, so yes, very good. Yeah, so you increase A, so that's true. Because you increase B, increase A, so increase sensitivity. So, and for this one, we know that when you use the UV visible and you have to use a solvent that not really like absorb that in that your detectable UV range, right? Okay, and also the sensitivity is about 1 picogram. So, UV visible is quite popular for HPLC. And when you're using that one, so the UV lamp, so theoretically it can use pretty long time. So you can always check the lifetime of the UV lamp in the detector. So, and also you have to be careful. So whether some dirt get into the surface of UV cell, because if you have some dirty things get UV cell, so, and then the surface inside not smooth anymore, you have some bumpy. So it can provides the place to generate some bubbles. Okay, if you get some little bit, still get some gas, small bubble inside and grow to be big bubbles. And part of the light energy may be lost, and the baseline can be quite noisy. So if the UV cell is dirty, so and make the noisy baseline and signal noise ratio to change. So that's why. So if that is case, then you have to clean this detection cell, but our technician will not let you do so. So they will handle that. And for that one, so if you happen you do that, so we can wash it, flush it with some detergent and hot water and so on. So it's something way to do that, the cleaned by direct injection of the following things. Well, another one, fluorescence detector. This is also something you have learned last semester, right? So you have the light source. We say we have to use very high energy light source for fluorescence. Why is that? Anyone still remember? Anyone still remember? Okay, so fluorescence, the signal equal to what? Relate to what? Signal is determined by what? Right? So what is P0? P0 is the intensity of the incident light source, right? Okay, so the signal is proportional to the energy of the incident light source. So here, that's why you want to using mercury or xenon lamp. So can be something like say high energy, okay? So, and then it hit it and also relate to the epsilon, so absorption coefficient of those fluorescence chromophore, okay? So, and we also see that detector is put so at 90 degree from the light source, because fluorescence, what happens is like say, it promotes the electrons, so jump from the ground state to the excited state, right? And then so it relax, and then sublevel, and then so it jump back. So that's why. So you have a larger energy gap for the jumping than jumping up than the energy gap for jumping back. So you have nominal excitation and then so you have the nominal emission. Okay, so which wavelength is longer? Which wavelength is shorter? Right? Okay, because more energy get excited. So that's why. So what we measure this one, emitted, right? We also emitted, so radiation. So you don't want it to be messed up or confused. So by the incident light. Yeah, very good. So that's why you put that into the 90-degree C angle to avoid the reference of the light source. Okay, thanks for answering question. So, and then, so this is how, so what to do so. So it's quite sensitive. So it can be the 10, so this one F gram is femtogram. So this is 10 to the minus 15th, okay, gram, sorry. So for that one, okay, so it's quite sensitive. So another one we use for LC detector, maybe this one is not the very common one you guys have seen before. It's called evaporative light scattering detector. This is more popular to use in slide solution chromatography. Okay, so it's called evaporative light scattering. From the name, you already know that. Based on light scattering, okay? But what I mean evaporative, okay? What happens like from the liquid chromatography, the mobile phase, and first it goes through the nitrogen gas nebulizer. So the nebulizer, what happened? Will nebulize the liquid into small droplets, okay? So and into small droplets. So that means, what happened is like, say, it goes through the mobile phase. Now it goes through the heated drift tube. That means it's heated at some certain temperature. And then what happens? The mobile phase evaporate. But so your sample droplets so remain. It's not really, so that means your sample must be significantly less volatile than the mobile phase. That is one key point. So your analyte must be significantly less volatile, so it can remain. And then only the mobile phase evaporates. And then once, so it's evaporated, so and it travels through the drifting tube, it reached the bottom, and then there's a laser light source hit it this way. And then will be detector put that at 90-degree C angle. Why we do that? Again, avoid interference, because once it hit the particle, the sample droplets, so the light will scatter in all directions. Light scattering is in all directions. Okay, of course, part of it will go to this 90-degree C, this angle, and be measured by this detector. And the amount of the light can be measured as proportional to, it's related to the mass of your sample. So it's mass sensitive. So this is mass dependent, okay? It's not really response to particular species. It's whatever. I don't differentiate A from B from C. Just all your sample. You may have contained 10 of them or whatever. So and then so this is your then you separate them, right? Okay, so it's connected to the LC. So LC will separate A, B, C separately. Okay, and if it's the C gets into the detector, and then so I only not correspond to the detector, not correspond to the structure of the C. It corresponds to what? It corresponds to the mass of C. Okay. So because the solvent evaporate, leaving fine particles analyte, and the particles themselves are detected. So the light scattering, because solvent evaporate, they become dry. That's why so they become particle. And then so response proportional to the analyte mass. Okay, it's response to its mass. Okay, and then so and let me see, and the same for all non-volatile solute. It's much more sensitive than the RI detector. Okay, so and if it came to that one is mass detector. The first step is nebulizing. Inside nebulize the column effluent LC, from LC pass through the needle and mix with nitrogen gas and form nebulized to form the fine droplets. And then the more biophase should be more volatile. So then, then the particle, okay? And then, so that's why, so they evaporates. And then, so they leave the compound small particles. And then, so once they reach to the bottom, so they were hit by what? They were hit by, so light scatter, the laser light. And then the light scattered by sample determined generated by the electric, okay? So signal. This is how that works, okay? So, and we use that one to do a lot of measurement, especially for those large compound, so with large molecular weight, so they measure that. So this shows you, so one of them to measure the polymer, you can see that. So anyway, we'll show a little bit more example later on when we talk about the size solution chromatography. Now we just give a overall. Let me see. Still have some time, right? Yeah, okay. So we can continue. And if it's not really for big ones, you can also handle even small ones. So this shows you the succinic acid. Succinic acid is carbon 4, only 4 carbon 4 diacids. Oh, you can show here 1, 2, 3, 4, right? Now, so this one, succinic acid. So even the small ones, right, correspond to, so it's mass because it does not really have a very good UV chromophore. So that's why it does not have a very good response in UV detection. But so as if we measure by the mass, it still can show. So short peak as long as it has enough mass concentration. Okay. Another very, very popular one is mass spectrometer. We see that. So mass spectrometer of HPLC consists of 3 different parts. So interface, so where the compound so enters the mass spectrometer and the ions are generated. And also can include the mass analyzer and also the detector. Detector is electron multiplier. So here just quickly go through because I know most of you already select the electrical course taught by Professor Tai, so about the mass spectrometer, right? Okay, so but here just refresh your mind. So the 2 ionization technique used for LCMS, including the electron spray ionization, ESI, and so atmospheric pressure chemical ionization. So we'll just take a look of them. So you can see that for electron spray ionization, ESI is quite popular. So so this is what is method to transfer ion from the LC eluent solution to the gas phase. Everything happened at atmospheric pressure for the ions, for this ionization to happen. So you can see here is the eluent HPLC column. Come here, and then so nebulizing gas apply. So and also it has high voltage. High voltage is about 2 to 5 kV. Okay, 2 to 5 kV apply on the tip, and then so and the droplets because the nebulizing. So the nitrogen gas nebulizing, and then so apply the high voltage here. And if it's positive ESI, then will be positive charge applied here. If it's negative ESI, it will be negative charge applied here. Okay, anyway, so the droplets now have the charge. And then, so also it has the heating gas, okay? So, and here, so the gas, because it's kind of the, evaporates, so it often evaporates. And then, so the charge density increase. Because the charge density increase, and then the charge so close to each other, they have the electrostatic repulsion. They're so close to me, okay? So they kind of like repulsion when you pull away each other. So that's why eventually once the charge density get really large, you have the Coulombic explosion, the Coulombic explosion, and then so those ions, the charge droplets get even fine or small droplets, okay? And then so the further, so dry that to be in the gas phase. So the solvent just further evaporates and then to become the gas phase ions and then get into the vacuum. Now again, so if the positive charged ions, so because if it's positive, if positive ESI, and then so here will be positive charge the tip, and then it will pull, it will hold back all those negative ions and then let the positive ions to get in. Okay, so if it's negative, CSI, if it's CSI, negative ESI, sorry. So, and then the tip will be negative charged, and it will pull back, it will hold back all the positive ions, and then and let the negative ions to get through. Okay, so this is if we have some negative ion so inside. So this is how to do that. And therefore, so if we're using the ESI, because it will be like say charged in liquid phase. So that's why we normally add some buffer into the mobile phase to make it more easily get charged. So in the ESI, so some of the acidic buffer, something like that one, you have to provide proton, right? So, and you can see that's why the ESI source must move ions from solution to gas phase. And you see how that happened. So it charged in the liquid phase, okay? So it charged in the solution, and then the solvent evaporates and then gets repelling and then Coulombic explosion and gets the gas ion, okay? So the transfer the gas phase ion transfer gas ion from atmospheric pressure, so here into vacuum. And so that's why I need two pumps to do that. One is the intermediate pump. So it give it to the intermediate pressure, and then so further another second pump to pull it to be even high vacuum. And then so yield ion beam, maximum current, okay, and then go through the quadruple. So, and it can vary significant among different analyte. So, and so that's why. So the one more easily get charged, that means more polar one, more easy to be ionized one, so have better response. And also, when you're using the solvent, you want, if you want, this is your target analyte, you want to elute it when the mobile phase is more easily get evaporated. Okay, so that's why if you want to analyze some certain compound, you want it at this retention time, so you have higher what? Higher organic fraction or higher water fraction, the mobile phase. You want the mobile phase to have a higher organic fraction, okay, when this your target analyte eluted. Why? Because when you get into ESI, I'm talking about ESI now, okay? You got ESI, so methanol, for example, methanol is much easier to evaporate than water, okay? So that will be, make it like say more easy to form this gas ions in ESI, okay? So, and more sensitive will make it. And condition optimize, we want to optimize the applied so ionization voltage, the temperature, the gas flow is what we are going to do normally in the mass. And then so, and the heated drying gas and also the capillary encourage the solvent to evaporate. And then so also limit the solvent analyte adduct formation. And then also we, because we want to facilitate the charge ion formation, so doing that one, so so that's why. So we normally adjust pH in the mobile phase. We add some of the modifier to make it so it can be acid or base to make it to be easily get charged. Okay, so that's why this one formic acid is often added. Okay, and then you can see ESI can form multiple charged ions, can consist of those, and then so that make it quite practical for those large molecular weight compound, because they basically, so now for this one is so M to Z ratio. What do we look at as M to Z ratio? So that is means, so here this one correspond to what? This one correspond to what? This correspond to M plus, so how many? So 15 hydrogen, right? And then so will be so 15 charge plus divided by Z is what? So Z is F15, right? Okay, so M plus that one divided by 15. So that's mass divided by 15. So this is how it looks like. So if I have more charge, it go to this way, right? Okay, so so this one, then Z can be determined by sequence of peak or by isotope the distribution. So this is, I think I won't go to detail. I think Professor I definitely have explained that in his class. Okay, so I think about time pretty enough. So how about we stop here? So we're going talking about the last one, the APCI, and then so we're going to start talking about chromatography, and then then we talk about the factors that influence the efficiency of HPLC. Okay, so let me see. So that's pretty enough because it's too late. I think too much information already had enough for tonight, right? Okay, so that's all for today. So so if you have any question, so you're more than welcome to send me email and ask me. Okay, so bye bye. So see you next week.